Now let's try to study the second kind of interaction among the waves. So now we just focus on the propagation of the one wave. But now let's consider in the space, there are more than two waves propagate. So they will interact with each other. Yeah? So this kind of interaction is so-called interference. It is a combined effect of the two waves. So there are actually two different kind of combinations. The first is the so-called constructive interference. That is that if you have the two waves overlap with each other, they always happen when the crest of the first wave overlap with the crest of the second wave. Therefore, you simply just sum the amplitude of the two waves together, it becomes one new wave. So this is a constructive wave because now it is simply 1 + 1 = 2, the concept like that. So the second kind of scenario, including all the rest, which is the destructive interference. That is, the crest of the one wave overlap with the floor of all the other part of the wave. So what happens is, this is a totally destructive interference, which is, when I say totally destructive, means the position of the crest for the first wave overlap with the position of the floor of the second wave. So these two positions actually overlap with each other, but now one is positive, one is negative. So they basically cancel each other. So the net result will be a pure cancellation. So the net wave is this. There's no wave anymore. So that's the reason I say it is a totally destructive interference. But if the crest of the first one is overlapping with other point of the second wave, it is still the concept of the destructive interference, but not a perfect one. So now, after the two waves combine together, they will become a new one. So let's try to study the most general case. So the first one is the one I just introduced you. So for the two transverse waves, if they are in the so-called constructive interference, then you can use the concept that the amplitude of the two should be summed together. But for the totally destructive interference, the net result will be just a straight line. So this is for the transverse wave. How about for the longitudinal wave? It will be the same. But now the amplitude is not in this direction. Yeah. Now the amplitude is along the direction of wave propagation. But still, if you try to add the two together, if the position of the crest is the same as the position of the crest of the second wave, then what you are doing is simply just summing the amplitude together, and you will see now what happens is that when you sum the amplitude together, it just makes the region which originally it is compressed. It is more compressed now, and the region which is rare, which is more rare now. However, if you try to add two longitudinal waves, originally the position of the crest is the position of the trough. Then when you sum these two longitudinal waves together, you will find out eventually you cannot even see any wave pattern there. So this is the so-called interference. Now let's try to study the third conceptual quiz today. And the answer is C. So the sound wave is a longitudinal wave, the light is a transverse wave. But no matter what kind of wave it is, they are intrinsically is a wave. Yeah? So interference is a property for all kinds of wave, not just for particular kind of wave. Now we are going to study a very important concept, so-called the standing wave. So what is a standing wave? Standing wave is the wave that actually they are oscillating, but your eyes will give you illusions, and since that the wave is not moving, the wave just stays there. So this reason people will say standing wave is fixed in location. But intrinsically, the wave is still vibrate. So now let's focus on the first scenario, which is the both ends fixed. So if you tied a string to both ends and these two ends cannot move, that is what we mean, both ends fixed. So this is a scenario actually in a lot of the instruments. So now when you try to use your finger to play around the string, they start to vibrate, yeah? So this kind of vibration is actually related to the standing wave. So the scenario B, this kind of vibration is the so-called the fundamental or the lowest frequency. What does it mean is that this one can produce the longest wavelength or the shortest frequency. And you definitely know that the frequency of the wave actually determines the pitch of that. And this is scenario B is the so-called the most fundamental one. And why I say this is the longest wavelength you can produce. So now we have to use the figure C to help you to refresh your memory. How do we define the one wavelength? It is from the point of the wave which repeats itself. So this is one wavelength. But if you compare the figure B and C, actually the figure B is just half of the wavelength. You can consider this half or this half. Okay, so you can basically consider that now the wave is also up and down. So they, no matter up or down, they only correspond in this first half or the second half. So therefore, the wavelength of this fundamental frequency is actually, the wavelength is twice the length of the string, because L now is half of the wavelength. Agree? So now the wavelength is 2 times the length of the string. This is how you connect it, the wavelength to the length of the string. But the most important thing is that this kind of oscillation, since it is fixed in space, but this is just the illusions. So now you can definitely produce different kind of modes. But now we should take a look about when we try to study the standing wave. So there's a point called a node. What is a node? It is when the standing wave propagates. You will see that it seems the wave is not moving. So there are several points. It seems it is always there. It is called a node. Okay? So you hold one end and this end is fixed. So the 3 points here are the so-called node. And for this one, you can basically say all the points are the node. And what happens in real life is that you are vibrating the spring and up and down. But what you see in your eyes is actually this. So you will see that it seems the wave is standing there. And it is mainly due to that the vibration of string is so fast. So the vision will be accumulated in your eyes. So therefore, the vision you see is actually the different kind of position of the wave, but at one time. So this is what you're going to observe in your eyes for the standing wave. So now, how do we describe about different mode of the standing wave? So we find out that for the 2 fixed end standing wave, then there's a pattern. The pattern is that no matter for the fundamental one or the second fundamental one, so now we will say this is n equal to 1 mode, n equal to 2 mode, n equal to 3 mode. They are always the integer of the half wavelengths. So this is one of the half wavelengths. This is the 2 times half wavelengths. This is 3 times half wavelengths. So n equal to 1 actually means that it is just 1 half wavelength. N equal to 2 mode simply just means 2 half wavelengths, which means it is 1 complete wavelength. So now you already see the pattern. And I already introduced you that the point which is not moving is the so-called nodes. And the part or the media which can have the maximum movement is the so-called antinode. So apparently in this n equal to 1 mode, the center is a position that can move maximally. So this is the position of antinode. Okay, so now you have the basic understanding about how we define the different mode of the standing wave and what is the node and antinode. So remember, so far the introduction is to both ends fixed. Now let's try to see the second scenario, which is one end is open and one end is fixed. So when the one end is fixed, it is the end with the node there. And one end is open, which means the particle can oscillate freely there. So it is an anti-node. So this kind of instrument can also produce the standing wave. So for examples, like the organ pipes or the bottle, when you blow through the soda bottles, you can produce some pitch. And they are all the concept of the standing wave propagate and produce in this kind of instrument. So let's try to study about more physics. So now, compare with the two fixed ends. Now the fundamental wavelength is no longer different. It's no longer the same. So you can see that because one end is fixed, one end is open. So the fundamental mode now is this. So what is this? This is just 1/4 of the wavelength. Agree? This is just 1/4 of the wavelength. So therefore, the wavelength of the fundamental mode is 4 times of the length of the pipe. So this is the first mode. And now this is the second mode. You may thought that the second mode is 2 times the 1/4 of the wavelength. The answer is wrong. The second fundamental mode is 3 times 1/4 of the wavelength. So why I say 3 times 1/4? So this is the first 1/4, second 1/4, and third 1/4. So this is a very unique and intrinsic difference compared with the two fixed ends. So they only have the odd number harmonic. Okay, so the pitch they can produce is only odd number harmonic. And finally, another surprise to you is that when the both ends are open, then both ends are the so-called the anti-node. And you will find out the wave pattern is different, but the result is actually very similar to the both ends fixed. Because now the fundamental mode for the both ends open is you have anti-node here and anti-node here. So from here to here, it is basically just half of the wavelength. This is just half of the wavelength. And now the second fundamental mode is that this is the 1, 2. There are 2 half wavelengths. So ideally, this is 1 complete wavelength. So n equal to 1 mole means one half wavelength. N equal to 2 mole is still 2 times half of the wavelength, which is 1 wavelength. So that's basically the result is the same as the both ends fixed. But you can see now because both ends are open, so it is anti-node, not the node on the both ends.